Okay, can folks in the chat hear me? Thank you. Okay, so as usual, remember to enter your seating survey, section 2 today. There are a couple of Piazza posts that are up relating to the midterm exam I want to point out to you briefly. So I'm going to, nope, try to get back over here. So if we look at the this post here, midterm exam 1, what we know so far, I will be updating this, including a revision log at the top to identify when new information is put on here. And I've got what information I can share with you about the first midterm exam. It's going to be covering weeks 1 through 4. We are currently in week 4, so this week's material is the last set of material that's going to be on the first midterm. The format is going to be online. I don't yet know if it's going to be Blackboard or Newton, but I will certainly get that information to you first. The resources you can use are pretty much any resources you want other than other people that you're talking to. So online textbook, your notes, Piazza threads, though I don't want you asking new questions on Piazza that are, how do I do this problem on the exam? So that would be the limitation there. Other resources you can look up, like a periodic table or an electronegativity table or something like that. What you don't use, like I said, are each other, and you don't go and ask people at the CIC or LAs or something like this about specific exam questions. You can ask such people about concepts. If you say, I don't understand how to determine when I should use face diagonals or body diagonals in a unit cell. You know, that kind of thing you can certainly ask, but asking specific questions that are from the exam is the main thing that you're not allowed to do. As part of the exam, you're going to be required to affirm an honor pledge that you've not used disallowed resources, meaning you haven't collaborated with somebody else on the exam itself. Date and time, I have a poll that is up to get your input on when you prefer it. What I'm trying to do is have it released sometime next week, late in the week. And I'll have it due sometime about 3 days following that release date. I'm going to design it to be completable in about an hour and a half. But I'm going to give you double that amount of time so that you're not feeling time pressure as you're doing the exam. So even though it's going to be listed as a 3-hour exam, the intent is that it's a 1.5-hour exam but if you have the need to go over that length of time, you can do so, okay? The poll, listed over here, midterm exam preferences. I have 5 options for what 3-day time frame I will allow, and some people have already started putting their responses in. This poll is going to close tomorrow morning, and so I'm going to take the results from that and take that into account when I make the decision about when it's going to be available and when it's going to be due. Okay, I didn't show that on, share the screen so that the online people could see it. I apologize for that. You can go to Piazza and find those two posts if you like. Okay. Group activity number 2, the Google Doc is due today at 5 p.m. I say here, seriously, do not divide up the questions among your group. So the design intent of these activities is that each question is a step along a thought process where you are constructing an understanding of the material. So if you divide up the questions among your group and you are assigned questions 10 through 20 or something like that, you're going to be on question 10 and you're not going to have the background of what happened in questions 1 through 9. And the questions are designed such that each question builds on the questions that came before. The intent is for you to be working together on question 1, brainstorm it, because some of these questions are not going to be obvious, have obvious answers, to come to a consensus on what the answer to question 1 is, and then together move on to question 2 and brainstorm towards a consensus on question 2 and work your way through the activity that way. This is a method of teaching that is known as Socratic instruction, or the Socratic method, named after Socrates from ancient Greece. A lot of the dialogues that were written by Plato about Socrates were written in the format of Socrates asking somebody questions. He never makes a declarative statement. He says, well, what do you think about this? And then what do you think about this? And through the process of asking those questions, the person he's talking to comes to an understanding of something they hadn't realized before. That's what's going on with these activities, and that's the goal of them. Okay. Group activity 3 in the syllabus would have it be due not next week, but the following week. That's when, probably right after when the exam is going to be due, and I feel like that's too close together, so I'm going to be pushing activity 3 back a week from that, so that you only, next week and the following week, you only have to worry about the normal content videos, homeworks, and the exam as the only added on thing for that. Okay, any questions on logistics before we get into content? Either from the class or from the chat. There will be some multiple choice. There will be some questions where you are doing a calculation and have to come up with a numerical answer. So in particular, you could imagine calculation questions on heat transfer kinds of things, for if you're doing a heating curve, cooling curve, something like that, and going through multiple steps and coming up with the Q for the reaction. There can be some calculations of things like packing efficiency or something like that. So there are a few places where you could come up with a numerical answer, and so that will be part of it. There may be some other, like ordering or multiple select or something like that. I am not going to have it for this exam. I'm not going to have any short answer essay kinds of questions on it, simply because I am looking for ways to streamline some of the grading that's going on so that I can catch up on the grading. I do like to have those kinds of questions, but given that I'm behind on the grading as I'm trying to get the exam together, I don't want to frustrate people by having even more of those things that are slow coming back to you. You had a hand up?
Yeah, and the ones where we have to put in a calculation, are we able to show our work so you can see how we got it?
Probably not. So, but what I will try to do is have the questions that have, okay, so for folks that are on the chat, the question was, for questions where there is a calculation, will there be a way for you to show your work for the potential of partial credit that's going on? I generally like to be able to do that, but again, that part is going to end up being a grading barrier as it goes forward, and so for this first exam I'm probably not going to do that. So what I'm planning to do instead is to have a calculation question have multiple components to it so that I can see what your intermediate values are as you go along. Okay, so so that while you're not showing the explicit work, the calculation questions will be guiding you through to some extent the steps of the process, and you can enter your answers for those successive questions. And I'm going to see if I can set it up, and this is one reason I don't know yet if it's going to be Newton or if it's going to be Blackboard. I'm going to see if I can set it up so that if you make a mistake in the first step and have an incorrect answer there, if I can make the automatic grading for the second step be dependent upon what your first answer was rather than what the correct answer was. So I'm trying to find a way to make that work so that you can get partial credit for the portions you do correctly. Will the test be graded on a curve? So it's going to be graded based on points, and those points are then going to get plugged in based on the formulas that are in the syllabus. Now, here's the thing. I have assigned point cutoffs for the overall class grade for this is where an A is, this is where a B is, this is where a C is. I view those as the highest I would possibly make those grade cutoffs. If it comes along as the semester goes on that people are not in general doing as well as I was hoping in particular areas, then I will absolutely take that into account and say, you know what, I probably made these components of the class harder than I intended, and so I could then shift the grading scale for the overall class downward in order to account for that. I have no interest in having a class where everyone gets a C or lower. I'm fine if I have an entire class where everybody gets an A. That's okay, as long as people are demonstrating and understanding the material. So, but the point there is that I'm going to be making that assessment towards the end of the class rather than on an assignment by assignment basis, because there are parts of this class, such as the content videos and the Newton portions of the homeworks, where it is possible for everybody to get 100%, right? Because you're demonstrating mastery of the material. And so if everybody has 100% on those, looking at an exam grade that somebody has, if the exams are skewed lower than that, which I assume that they will be, looking at that and saying, well, is that an A, is it a B, or is it a C on the exam grade doesn't really matter, because what it is a number of points that go into the final course calculation. Okay, so I don't think of any individual assignment as having a letter grade. I think of an individual assignment as contributing points to the final grade. This is one reason why I'm going to be providing you sometime shortly after the first exam with a grade projection spreadsheet where you can put in the grades that you have and then project forward if this is what's, how I continue. If my first exam score is exactly what all my other exam scores are going to be, it'll calculate for you what your total score would end up being at the end. And so that kind of, in my mind, takes the place of thinking about individual assignments as having letter grades. Okay. Any other logistical stuff you want to chat about before we move on to content? Okay. So, actually, one other thing. Upcoming due dates I need to go over. Okay, so today is the small group activity number 2, the Google Doc portion. Tomorrow at 5 is small group activity number 2 quiz. Remember to do that, because that's where the majority of the grading effort is going into that. Content video quizzes, you'll notice here that there are 6 content videos, which seems like a lot, but you'll also notice that many of them are extremely short. So the last 3 are around 2 minutes each. And this is a question I have for you guys. If any of you have any feedback for me, send it to me via Piazza, or if somebody wants to put up a poll, you could do that. I am curious about whether your preference is to have more shorter videos or fewer longer videos. The colligative properties things, you see that there are 4 videos of it, which together are about 10 minutes. So it could have been one 10-minute video instead of 4 2 or 4 minute videos. I don't have a strong preference on that myself, and so if any of you guys do and want to, set up a Piazza poll so we can see what the class thinks about it, I can take that into account in future videos as I'm putting this together. Okay, and then Friday is homework 4. There are 4 parts to this one. A couple of them are really short. And there is no supplementary question this particular week, again, because I'm trying to catch up on the grading. All right, let us move on to some muddiest point stuff. So I'm going to start with the topics that are directly related to this small group activity that you're working on. There were quite a few of these topics that were covered in yesterday's class. The video for that is up along with the usual timestamp index on it. So if you have a particular question on that we're not covering today, if you're working this afternoon on this activity, for example, that's a great resource to go back and see some of the other things we talked about. And if once we're done with the topics, the muddiest points we have for today, if somebody wants to bring up any of those same ones, I'm happy to go over them again. That's not a problem. Okay, so let's look at some of these small group activity questions here. The first one here was looking at the question that's looking at the 200C arsenicum album remedy and how large a volume you need to have a single arsenic atom in it, and suggesting that it would make sense to put this in units of cubic light years, which is kind of frightening if you think about it, but that's kind of the point of the activity. And then I give you the length of a light year. So this is very simply a dimensional analysis problem. And so, as I mentioned last week, I put together a video on dimensional analysis that doesn't have quizzes associated with it. If you're not comfortable with dimensional analysis, that's a great place to go for it. So what I'm going to do is pick a random very large number, and I will show you how you go through this kind of calculation with that large number. So let's suppose that we have a volume that we get that is going to be 10 to the let's do 10 to the 100th milliliters. Okay? And we need to know what that is in cubic light years. Okay? So what is it, if we wanted to go from a volume that is in milliliters and go to a cubic unit of volume, like cubic meters or cubic somethings, what is the direct conversion we have for that? Yes? Correct. 1 milliliter is 1 cubic centimeter. So what we do, we want milliliters to cancel, so milliliters goes into the denominator. And this is a cubic centimeter. So milliliters cancel, 1 and 1. Now, centimeters is a little bit of an awkward unit. Very often it is useful to transition from this to meters before you go on to whatever the next thing is you're dealing with. All right. So, how many centimeters are there in a meter? Yes. We'll get to that in a second. Okay. How many centimeters are there in a meter? 100. So 100 centimeters in a meter. Now, this is going to cancel out one of the three, exactly as you were suggesting in the cubed part. So what we need to do is multiply by this conversion factor 3 times. So times 1 meter over 100 centimeters times 1 meter over 100 centimeters. And so now that cubic part cancels with that. And you're left with meters, 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 or cubic meters. Now, you can write that, if you prefer, as 1 meter over 100 centimeters cubed. My problem with doing that is once I have my long dimensional analysis line, I will sometimes overlook the fact that there's this cube here, and I'll forget to divide by 100 cubed. Alternately, you could figure out what 100 cubed is, and you could put this in as 1 meter cubed is I think I did that right. Yep. Put it in as that. All three of these are mathematically equivalent. Let me bring it up. All three of these are mathematically equivalent. This is the easiest one to write down, and if you're confident that you can remember to use the cube as you're going through, it's certainly the most efficient way to go. This one is the most explicit. So choose which way you want to do it, however you like. Okay. All right. So we now have this in 2 cubic meters. Next, we know from here that we have some relationship between light years and kilometers. So we need to get this into kilometers before we can get it into light years. So how many meters are there in a kilometer?
1,000.
1,000, correct. All right, and we now need to do that 3 times. So this time I'm going to write it as a cube because I've explicitly mentioned this, so I'm probably not going to forget it. Okay, and so meters, 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 and meters cubed there cancels. So we now have cubic kilometers. Now for each kilometer, for the kilometers, we know that a light year is 9.5 times 10 to the 12th kilometers. So 9.5 times 10 to the 12th kilometers, and I'll do Ly for light year. Okay, and then this is going to have to be cubed as well, so that cubic kilometers get canceled, and we end up with something in cubic light years. Okay, and so all you do now is you actually do the math. So you take 10 to the 100, divided by 100, divided by 100, divided by 100, divided by 1,000, divided by whatever 9.5 times 10 to the 12th cubed is. I'm going to assume that you have a way to type that into a calculator. If your particular calculator doesn't handle exponents this high, as many scientific calculators do not, then I recommend going to the website Wolfram Alpha. That can handle pretty much any size you want. And so you can just type in the equation you want there, and it will handle it just fine for you. Okay, does this general approach to dimensional analysis make some sense? Okay, any questions, any follow-up questions on this aspect of the questions, of the activity? Okay. All right. So there's a clarification on wording. How many ions of arsenic are present in 1 milliliter of that 10C, or in a later question, 30C sample? And so the clarification question is, does this mean how many atoms? In this case, yes, it does. The reason I use the word ions is because in this solution, the arsenic atoms are charged. So saying ion is more specific, but yes, it is talking about how many atoms there are. And so yes, you use Avogadro's number to get from moles to number of atoms or number of ions. So that's all that's going on there. And then since this is a charged species, when we're writing it down, do we need to include the 3 minus? Generally, that's a good idea, yes. It's generally a good idea to include the charge on the ion when you are writing it down. Okay, so and that's the list of muddiest points on this small group activity that came up, which were not the muddiest points that I handled yesterday. Are there any other specific questions on this small group activity you would like me to go over now before I go on to the other muddiest points? Yes, in the back.
I just wanted to clarify with the arsenic atoms.
Yep.
Are there 2 of them in the molecule?
Right. So what you are looking at when you make the solution is you are taking arsenic trioxide, which has this formula, and you are dissolving that into your water. So once you do this, you have individual arsenic ions, each one of which has a 3 minus charge. So in that first step, where you're saying I'm starting with 1 cubic centimeter of arsenic trioxide, and you have a density of arsenic trioxide so that you convert it to grams, you then need to, so you have cubic centimeter of As2O3, you're going to have grams of As2O3. Okay, so I'm going to take you through the dimensional analysis we would do for this. Cubic centimeters of arsenic trioxide is going to be canceling, and I'm not putting in the number because I don't remember off the top of my head what the density of arsenic trioxide is. What matters more here is understanding the procedure, so I'm going to assume that you can plug the numbers into your calculator. If you have grams of arsenic trioxide, you can then go from grams of arsenic trioxide to moles of arsenic trioxide. How do you do that? What do you use for this? The molar mass. So it's going to be 1 there, it's going to be whatever the molar mass is here. And then we recognize that for every mole of As2O3, once it dissociates, you get 2 moles of As3 plus ions. Yeah, so this question was wrong because it says 3 minus, that should be 3 plus. So that is the point where you take into account that that there are 2 ions of arsenic per formula unit. Does that make some sense? Okay. Any other clarifying questions on the small group activity number 2 before we move on to other topics? Okay. Since there have been a number of people who have demonstrated some issues with dimensional analysis, there's one subtlety here I want to point out. You'll notice that at every step, I am including the substance as part of the units. That's extremely deliberate. If you only put in cubic centimeters and then cubic centimeters and grams here, you're losing track of what it is that it is grams of. And so it would be very easy at this point to stop at this step and say, well, I've got moles, so I'm done. Not realizing that you are a factor of 2 off because you didn't go from the formula unit to the ion itself. So it is, I mean, as a professional chemist, I do these kinds of calculations for my work on a daily basis. And I still write out the full units, including the substance, at every step along the way, because doing that prevents mistakes. Okay. All right, so let's talk about some solution stuff, since that is at least somewhat related to the small group activity number 2 things. We got a question about the Van't Hoff factor content video. So if any of you have not made it to the Van't Hoff factor content video yet, that one is talking about, for colligative properties, how do we determine how many solute particles you get for every formula unit that dissolves. So, for example, the example I use in the video is, I think, aluminum sulfate. So aluminum 2SO4 3. And when this dissolves, we get 2Al3 plus and 3SO4 2 minus. So we end up with 5 ions per formula unit. And so when we are looking at the concentration measures for colligative properties, if we determine that something has, say, 0.1 molal aluminum sulfate, we would have to multiply that by 5 in order to find what the concentration is in terms of dissolved units. And it's the dissolved units that are what determines the colligative properties. This 5 here is what's called the Van't Hoff factor. And it is given the unfortunate symbol lowercase I. I say unfortunate because that's also the imaginary number. And so it can get confusing at times. Now, the problem with simply looking at the formula units and saying, well, there are 5 there, is that there's a physical phenomenon that happens that makes the 5 not perfectly accurate. That physical phenomenon, find the right sheet here, is this. So because the 2 different types of ions that you have are oppositely charged, there's an attraction between them. And so occasionally, a pair, an ion pair will form where you have a positive ion and a negative ion, and they stick together for a little bit. It's a dynamic equilibrium, so there will always be some, and they are frequently forming and breaking. But when they are together, when this is formed, this acts as a single unit in terms of colligative properties, rather than them acting as separate units when it comes to colligative properties. So the experimental values for the Van't Hoff factors I tend to be lower than what is predicted just from the value that you would get from looking at the formula units. So a comment was made that ions in dilute solution are generally far apart, and they also rarely exist in ion pairs. and trying to understand the connection between those two. This is comparing dilute solution to concentrated solution. So if you think about this happening, and if you think about this as a dynamic equilibrium, if you think about these ions coming together and then coming apart, the more concentrated your solution is, the more frequently they are going to be running into each other. So the more frequently they will form an ion pair. So what you would predict is that at high concentrations, the experimental Van Hoff factor should be quite different from the predicted. But at low concentrations, at very low concentrations, where the ions are almost never running into each other, the Van Hoff factor should be very close to the predicted Van Hoff factor. Because the mechanism for the deviations from the prediction have to do with oppositely charged ions finding each other and then sticking together. And if you simply don't have very many, then the frequency with which they find each other is going to be very low. Does that general trend make some sense? Yeah. Okay. Any clarifications on that aspect, on the Van Hoff factor issue? Okay. All right. Let's talk about dynamic equilibrium a bit, of which ion pair formation is an example. Solubility is an example when you have the solute in equilibrium with the solid at the point of saturation and so on. And there's a question that I asked in the dynamic equilibrium content video that was asking about the notation for a dynamic equilibrium, where there are arrows over each other compared to a double-headed arrow. So if we look at, say, here's what I wanted to do. NaCl solid is in equilibrium with Na plus aqueous and Cl minus aqueous. The notation we use is an arrow over an arrow. And frequently, when we hand draw these, we will do a single-headed arrow rather than a double-headed arrow. It's okay. It's hard to find that format in like PowerPoint and Microsoft Word and stuff. So frequently you'll see full arrows, but it's still an arrow over an arrow. And this is contrasted with a double-headed arrow, which is this. This has a different meaning in chemistry. Does anybody remember what this meaning is? It was from Chem 111. Let's hear. Can't remember the name of it? Okay. When you have a bond that moves around. Okay. So this is what we use when we are looking at resonance structures. So an example you probably looked at was the Lewis structure for ozone, because everybody uses that one, where that is one Lewis structure. And then you could have a Lewis structure where it changes which two oxygens have the double bond between them. And so the idea of resonance structures, you may remember, is that reality is kind of an average of these two. It's not saying that it's sometimes this and it's sometimes this and it switches back and forth. No, that is not what resonance structures mean. Resonance structures mean that the real structure is kind of an average of these two. So even though we can't really do this with Lewis structures, you might draw it something sort of like that, where the electrons are kind of partially in this bond and partially in that bond. Oh, I'm sorry. Thank you. So you might draw it something like this, where the electrons are partially in this bond or partially in this bond. Okay. So this symbol with the double-headed arrow is what is used to connect Lewis structures that are resonant structures of each other that contribute to an overall understanding of what the molecule acts like. You need to make sure that you do not use this when you're talking about equilibrium. Equilibrium means there is a forward reaction and there is a reverse reaction, and they are happening at the same speed so that the concentrations of the reactants and the products are not changing. It's a dynamic process. Does that notation difference make sense? Okay. Any clarification questions? All right. Okay, there was also a question on relating to dynamic equilibrium. It's talking about crystal growth. So there was a discussion in the solubility content video that was talking about supposing that you have sharp corners or edges of crystals that are dissolving faster than flat surfaces or sides. And also suppose that flat precipitation happens faster at the edge. I don't think I typed that right. Also suppose that precipitation happens faster at the edges because the added molecules or ions fit along the grooves than it does in the middle of a face. Which prediction would these assumptions best support? And the answer is salt crystals will grow more regular due to preferential dissolution and growth at the edges. And so there was a question about trying to visualize what's going on here and why it has that effect. So what this idea is getting at, I'm gonna flip this over. So here is a picture of a crystal, and you'll notice that it's not a single crystal. You have portions of it that are like sticking up, and you've got sort of sharp edges and then sort of little steps that are happening at various points along it. Okay, so the idea here is that comparing this to a crystal that is perfect in that you have a single crystal with flat surfaces and only edges between those flat surfaces, this has a lot more sharpness to it. There are a lot more sharp edges, sharp corners and such. What's going on physically in the dynamic equilibrium is that you've got a structure like this where you can have atoms or molecules being added or ions being added, or you can have them being taken away at these points. And let's think about the process of what's happening. The process is that when you have let's think about the dissolution process first. If we look at, say, this block right here, which is kind of in the middle of a face, there aren't very many places where solvent molecules can get to it, only along the surface. But if we look at this corner one, we can get solvent molecules on the top, on the front, and on the side. And so those then can help pull away the ion or molecule. Whereas along the surface, it can't really grab onto it very effectively, right? Because remember, almost all of these interactions are governed by attractive forces. And so in this case, there are a lot of attractive forces between this particular block and the surrounding blocks, and there aren't very many attractive forces between this block and the solvent. Whereas here, there are still quite a few attractions to the block, but there are a lot of attractions to the solvent as well. Okay. If we then imagine a new block coming in and depositing onto the surface somewhere, if that new block came in over here, it is still going to be mostly surrounded by solvent. There's only going to be one face of the block that comes in that is going to have its attractions replaced by attractions to the growing crystal. Whereas if it comes in up here, it's going to have a lot of its attractions replaced by attractions to the crystal. So deposition here in this groove that's formed is going to be a lot more stable than deposition on a surface where it's going to be very exposed. So these two factors working together mean that either an edge like this is going to fill out through deposition, or it's going to get etched away and go away. And so a crystal that starts out like this, if it's in dynamic equilibrium, is going to transform over time through sequential additions and dissolution steps into crystals that are much more uniform and have larger regions of uninterrupted surface. So that's what that question is trying to help you visualize. Any clarifications on that idea? Okay. So let's talk now about energy and entropy in solution formation. In particular, there are a lot of questions on Newton about, there are a lot of questions on Piazza about this because you are being asked some questions on Newton that I wish I could delete, but I don't seem to have the ability within an adaptive learning homework system to say I don't want these specific questions, which is frustrating, but we have to deal with it. The problem is we haven't introduced the material yet that you would need in order to take this information. Yes. I think this is last week's homework. Yes. There, I don't think there is. No, I think this week is almost entirely colligative properties and stuff. So I will very briefly go over what you need in order to do one of these calculations if you want. It's very quick, but I am not going to hold you responsible for this on an exam until after we actually introduce this idea once we get to entropy for later exams. Okay, so the idea is, you remember that we said spontaneity was about when delta H was less than 0 or delta S was greater than 0. But the problem is what happens if they point in opposite directions. Well, this is enthalpy. This is entropy. There is a related quantity, G. And we, just like these, we talk about changes in enthalpy or changes in entropy. Here we talk about delta G. G is called Gibbs free energy. We'll talk about why that's called that later. And delta G equals delta H minus T delta S, where T here is the temperature, and it is measured in Kelvin. Okay. So that means temperature here is always positive. The Gibbs free energy gives us strict spontaneity rules. If delta G is less than 0, spontaneous. If delta G is greater than 0, not spontaneous. And that's it. That tells us spontaneity. Now, how does this relate to these criteria here? Well, if we didn't have to worry about the delta S part, well, delta H less than 0, meaning spontaneous, is the same as delta G less than 0, right? If we didn't have to worry about the delta H part, we have a negative T delta S. And so delta S greater than 0, when T is greater than 0, means delta G would be less than 0, which is still spontaneous, right? So this one thing encapsulates spontaneity, but it tells you what to do if they're pointing in different directions. So if they're pointing in different directions, then at low temperature, where T is very small, then delta H is what determines whether it's spontaneous or not. At high temperature, then where T is big, then negative T delta S is what determines whether it's spontaneous or not. So if delta H and delta S point in different directions, this equation here tells you at what temperature it switches from being spontaneous to being non-spontaneous. Okay. Now, I know we have not gone into this. So if you ever, before we cover this, run into this kind of question again on Newton, this is how you do it. We also haven't gone into why. And I recognize that, and I know it's frustrating to have a discussion of this is how you do something without the discussion of why. The explanation for why is going to take a while, and so I'm going to put that discussion off. Okay. So I'm going to call that part done. I'm going to call this part done because this is asking the why question. And at all we care about for spontaneity in terms of solution formation is, does it happen? So we will get to the why at a later point, and we'll deal with that at that point. What's the point? What do we mean by spontaneous? That part is actually a good question. Not spontaneous means it does not happen. The reaction does not happen at all. It is impossible for it to happen. That would be like taking carbon dioxide and water vapor and turning it into gasoline and oxygen. That reaction does not go that direction. It is spontaneous the other way, where you take gasoline and oxygen and you go to carbon dioxide and water vapor. Spontaneous means it can happen. Doesn't mean it will happen. It means it can. So why might it not if the reaction rate or speed is too slow? So it is spontaneous for diamond to turn into graphite. It is ridiculously slow for that to happen, so slow that we never see it happen. So spontaneity here tells you, can it happen? And if the answer is no, that's a hard and fast no. If the answer is yes, then you have to look at other things to see if it will happen. Okay. There's also the question here about Hess's law and how does it relate to energy and entropy in solution formation. So Hess's law was something that was covered in Chem 111 in the thermochemistry chapter with relation to delta H values. And the idea of Hess's law is that enthalpy is a state function. Okay. A state function here is something being contrasted with a path function. So the analogy that I use for this is we've got a mountain and we've got a hiker down here. There are lots of ways the hiker can get to the top of the mountain. The hiker could climb straight up the mountain. The hiker could circle the mountain a bunch of times and get to the top. The hiker could get picked up by a helicopter. And dropped on top. However the hiker gets to the top, her change in altitude will be the same. because altitude is a state function. It depends only on the starting condition, the final condition, not on what happens in between. A path function would be something like distance traveled. Okay, and so by each of these three methods, the hiker will have gone a different distance, but the altitude change is constant. Enthalpy, because it's a state function, means that however you get from reactants to products, the delta H will be the same. And so if it doesn't even matter that you didn't go by that alternate path. Even though we did, this hiker did not ride a helicopter to the top of the mountain, if you somehow used a helicopter to measure the difference in altitude, that would accurately tell what the change in altitude for the hiker was, right? So what that means is that for any reaction we have, we have A goes to B, we can construct an alternate pathway if we get to the same place, then the delta H for this path has to be the same as the delta H for that path. Now, why would we want to do that? Well, maybe these steps that we have in this alternate path are things that we know the delta H for, even though we don't know the delta H for this. Or maybe doing this process breaks it down into steps where at least we would know, is it going to be positive or is it going to be negative? And so that tells us something about the nature of what's happening going from A to B. So that's what we're doing here. It turns out that these other thermodynamic functions that I mentioned up here, entropy and Gibbs free energy, are also state functions. So we can use Hess's law on them just the same way. So where we used that in talking about solutions was to say, let's take sample 1, where we have all of our molecules together. So this could be a liquid. And we have solution 2, where we have all the, sample 2, where we have all the molecules here. And we want to mix them. We'll do this. Into a solution of the two. Like this. But we decided that we could get there by an alternate method. We could take this, separate it out, so that we now have overcome some of the intermolecular attractions between the blue molecules. We take this one, and we do the same thing to this one, so we spread out the black molecules. So all that's happening here is we're breaking some intermolecular forces. Same thing here. So these are going to be endothermic processes. Then we take those together and we mix them. And so all you're doing in that step is you're looking at the forces of attraction between the blue and the black. So even though we don't make a solution by doing this, the total delta H for doing that is going to be the same as the total delta H for doing this, because it's a state function. Same thing for entropy. And thinking about it in these terms, doing it this way instead of this way, lets us separate the ideas in our heads of the attractions between solvent molecules, the attractions between solute molecules, and the attractions between solvent-solute molecule combinations. So that's why we cared about Hess's law when it came to solutions formation. Any questions on that? Okay. All right, the last muddy point that we have is going all the way back to intermolecular forces and people still expressing some confusion over being able to determine which forces are present for a molecule, especially things like ion dipole as compared to dipole-dipole. So I want to do a couple of things with this. I want to try to attack this in a slightly different way than I have in previous classes. It seems as though there are sort of two bits of confusion that people seem to have. One is that when we're talking about intermolecular forces, we are talking about the interactions between one molecule and a neighboring molecule. You don't, when you are thinking about intermolecular forces, don't think about one molecule. Think about the interactions between that molecule and another molecule. Now, if you're talking about a pure substance, it will be another of the same kind of molecule, but it is nonetheless a separate molecule. Secondly, there seems to be a lot of confusion about how to identify which properties a molecule has, ion or dipole or something of this sort. When you're trying to identify the forces, I think of it in terms of a grid. And so this is one molecule. This is the second molecule. And so what you, in order to determine, do I have ion dipole interactions, what you do is you say, does one molecule have ionic character? And does the other molecule have dipole character? If yes, then yes. That's what you do. So the one thing that is not captured in this chart is hydrogen bonding. Which is which is just the special case you have to remember to add in addition to this. Okay. Now, how do you know if a molecule has induced dipoles? Every molecule has it. If it has electrons, it has induced dipoles. End of story. Because electrons can be polarized by anything that comes in near it. And that polarization is an induced dipole. So you always have that unless you're dealing with H+ in a vacuum. Okay. Does it have a dipole? To find out if it has a dipole, you look at you have to look at the Lewis structure. You determine, are the bonds polar? If the answer is yes, there are polar bonds, then you look at the geometry using VSEPR theory to see, do the bond dipoles cancel out? If the answer is no, they do not cancel out, then you have dipoles. End of story. Do you have ions? I've actually been surprised that this seems to be one of the biggest points of confusion, because I will ask, I'll put up a list of things we're trying to compare, and I ask, are there any ions here? And I get more blank stares on that than I do on anything else. So that one I want to actually spend a moment on to make sure people understand how this works. if you look at the periodic table, we've got here 3 different colors. It's a different color scheme than the one up on the wall, but it's still divided into the same categories. We have metals, which are yellow on this one that's on screen. We have nonmetals, which are the green ones, and we have the metalloids, which are blue or purple or something. I'm partially colorblind, so I know it's somewhere in that neighborhood, which have some of the properties of each. What's the main characteristic of a metal with respect to its valence electrons? It wants to lose them. I would describe that as it doesn't hold on to them very tightly. They are only loosely bound. Okay. What is the main characteristic of a nonmetal in terms of valence electrons? What's that? It's okay. I still couldn't hear you, I'm sorry. They want more electrons, okay? They hold on to valence electrons extremely tightly, okay? And notice that that correlates with electronegativity, right? Electronegativity is high over there, and it's low over here. It's the same thing, same ideas. So if you bring a metal and a nonmetal together, the nonmetal is going to steal the metal's electrons. You get covalent bonding when you have 2 nonmetals together because they're both trying to hang on to those electrons, right? Covalent bonding is not ions. Ions are when one thing grabs electrons and something else gives them up. That's metal-nonmetal. Okay. Mostly, and we'll get to that. So if you see something that has a metal and a nonmetal, it is probably ionic. Sodium chloride, where's sodium? Where's chloride? Right there. Na+, Cl-. Cesium oxide. CSO, CS2+, O2-. Ionic. All right? Now, I recommend finding a table like this and keeping it handy for yourself. This one that I copied out says to memorize. I'm not big on memorization. I would suggest that you find a chart like this and keep it. I can probably put up a link to this one. This has a list of common ions. And so the monatomic atomic cations up there, most of those are metals. The monatomic cations with multiple oxidation states down here, those are also metals, okay? The negative ones, the anions up there, those are nonmetals and in a few cases metalloids. But, so those are the negative ones. The tricky part comes in with the polyatomic ions. But usually the polyatomic ions, like a sulfate or something like that, is going to be connected to a metal. And so if you see a metal and then something that isn't a metal next to it, you probably have a polyatomic ion. Okay. The one exception that is common is ammonium. This is a positive ion, NH4+, that is non-metallic. NH4+. That is the only common positively charged ion that is non-metallic. There are some very uncommon ones, but that's the only common one. So I'm asking you to remember one of those. So if you see NH4 something else associated with it after that, it's probably ionic. In pretty much any other case you're going to deal with, you're looking at a metal with nonmetals, and then it's ionic. So that then takes us back to this. So if we look at a particular compound and we say there are no ions, boom, gone. And in fact, that one goes away as well. If we say, yes, it has a dipole, then we have this, 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 because everything has induced dipole, and then you determine does it have hydrogen bonding. Now, some of these are duplicates. In dipole-induced dipole and induced dipole-dipole, those are the same thing. So we only really look at those three. So it's going to have dipole-dipole interactions, dipole-induced dipole interactions, and induced dipole-induced dipole interactions. And then maybe hydrogen bonding. Does that procedure to think about this make sense? Yeah, okay. I am out of time, so any clarifying questions? Okay, did that help in talking about how to determine if things are ions or not? Yeah. Yes. With the, oh, this? Okay, yeah, I can do that. What's that? Yeah, I do use this very same, I may have them in the other order, but I have this very same thing in the very first video. But yeah, I'm happy to make a sheet of this and put it up for you. I will also provide a link to this list of the common ions. Yeah, and I'll get that out today.
Problems I've seen on my exam, no problems with others, but like good key concepts.
All right. Thank you, everyone.